And if we now look to the thermal behavior, it's similar to what you could see if you use a thermal camera. It's a view from top of the complete setup. You see here the super SO8, some copper traces, and of course the complete area of the lead frame, the aluminum carrier. You see after 50 milliseconds that just a part of that board is a little bit hotter than the other area. Remember, we had internally a time constant of 44 milliseconds. That means inside the part, the temperature is expected to be much higher. Let's see how much higher. Okay, after 100 milliseconds, you see that also on top of the part, the mold compound, the plastic, you see also the temperature rise. After 400 milliseconds, you see again another detail. Here on the right bottom corner, you see the gate connector. Of course, there is no heat dissipation, so this part is always a little bit colder. After 700 milliseconds, the temperature rise is higher, of course, and after 1 second, we already have a temperature which is much higher than 110, 120, but we don't know yet what happened inside the part. Okay, next step would be to look to the bottom of our part, to the lead frame. After 50 milliseconds, you see the difference to the view from the top is already there. After 100 milliseconds, the temperature is not really homogeneous, but it's not that inhomogeneous like on the IMS board. After 400 milliseconds, you see already some colder dots here, and after 700 milliseconds, you see here these two dots. These are the connections of the copper clip to the chip. Of course, this cools down a little bit, these small areas. After 1 second, the chip area itself, or the area below the chip, is more or less completely heated up to 140 degrees Celsius. Last question, of course, is how much hotter is the chip inside? Next picture shows the chip temperature after 1 second compared to the bottom side of the lead frame. You see here the difference is just 3 or 4 Kelvin or degrees Celsius. From our simulation program, we can derive the complete time behavior. What we see here is that first, as already mentioned, the temperature difference between lead frame and chip is negligible. It's around 4 degrees Celsius. We see another thing. Between starting point and 100 millisecond, there is a strongly nonlinear behavior. Remember this 44 millisecond time constant of the part itself. After 100, 150 or 200 milliseconds, the complete thermal behavior is linear. This can give us additional hints if the problem we have is not exactly 1 second with 25 watts. For example, if we just have 500 millisecond pulse with 25 watts, we just can read here the temperature is around 120 whatever degrees Celsius. If the pulse is longer, we just can increase the length of the graph to the right side. Or if the power rating is different, we can shift that graph with the ratio of the power losses compared to our 25 watts. If your result is that the temperature after your power pulse is too high, of course there are different possibilities to solve that problem. If you can't avoid this power pulse, a first possible solution would be to choose an IMS board with a lower thermal resistance, but maybe too high costs are then the problem. A second way to solve this problem is to increase the thermal capacity of the complete arrangement. Of course, an increase of the area of the lead frame itself wouldn't be the solution. As shown on the last pages, the time needed to fill that thermal tank is too high compared to our 1 second problem, the overload condition. Another idea, of course, could be to increase the thickness of the aluminum carrier. This indeed will decrease the maximum chip temperature, and it could be the solution if higher costs and additional space are acceptable. Infineon offers a third solution with no issues regarding space and weight: a MOSFET with a lower RDS on. We started our investigation with an 1.6 milliohm part, the BSC 016 NO3 LS. Looking to the huge Infineon portfolio, we will find a MOSFET from the same family, in the same package, and the same voltage rating with a much lower on resistance, the BSC 011 with 1.1 milliohm. If you have to go to higher switching frequencies, another part offers additional features, the BSC 011 with a suffix I at the end, with nearly the same RDS on, but with a monolithic integrated Schottky-like diode on the chip. This MOSFET offers an optimized switching behavior, especially at higher frequencies. I hope you enjoyed the last few minutes. If you need further information, you can visit us on our website. Thank you for your attention and your time. Please visit us again if you want to.